Chromium. Chromium is a chemical element with symbol Cr and atomic number 24. It is the first element in group 6. It is a steely-grey, lustrous, hard, and brittle transition metal. Chromium boasts a high usage rate as a metal that is able to be highly polished while resisting tarnishing. Chromium is also the main component of stainless steel, a popular steel alloy due to its uncommonly high specular reflection. Simple polished chromium reflects almost 70% of the visible spectrum, with almost 90% of infrared light waves being reflected. The name of the element is derived from the Greek word chromu alpha, chroma, meaning color, because many chromium compounds are intensely colored. Ferrochromium alloy is commercially produced from chromite by silicothermic or aluminothermic reactions and chromium metal by roasting and leaching processes followed by reduction with carbon and then aluminium. Chromium metal is of high value for its high corrosion resistance and hardness. A major development in steel production was the discovery that steel could be made highly resistant to corrosion and discoloration by adding metallic chromium to form stainless steel. Stainless steel and chrome plating together comprise 85% of the commercial use. In the United States, trivalent chromium ion is considered an essential nutrient in humans for insulin, sugar, and lipid metabolism. However, in 2014, the European Food Safety Authority, acting for the European Union, concluded that there was not sufficient evidence for chromium to be recognized as essential. While chromium metal and Cr ions are not considered toxic, hexavalent chromium is both toxic and carcinogenic. Abandoned chromium production sites often require environmental cleanup. Chromium is the fourth transition metal found on the periodic table, and has an electron configuration of 3d54s1. It is also the first element in the periodic table whose ground state electron configuration violates the Aufbau principle. This occurs again later in the periodic table with other elements and their electron configurations, such as copper, niobium, and molybdenum. This occurs because electrons in the same orbital repel each other due to their like charges. In the previous elements, the energetic cost of promoting an electron to the next higher energy level is too great to compensate for that released by lessening interelectronic repulsion. However, in the 3D transition metals, the energy gap between the 3D and the next higher 4s subshell is very small, and because the 3D subshell is more compact than the 4s subshell, interelectron repulsion is smaller between 4s electrons than between 3D electrons. This lowers the energetic cost of promotion and increases the energy released by it, so that the promotion becomes energetically feasible and 1 or even 2 electrons are always promoted to the 4s subshell. Chromium is the first element in the 3D series where the 3D electrons start to sink into the inert core, they thus contribute less to metallic bonding, and hence the melting and boiling points and the enthalpy of atomization of chromium are lower than those of the preceding element vanadium. Chromium is a strong oxidizing agent in contrast to the molybdenum and tungsten oxides. Chromium is extremely hard, and is the second hardness metal behind boron. Its Mohs hardness is 8.5, which means that it can scratch samples of quartz and topaz, while be scratched by corundum. Chromium is highly resistant to tarnishing, which makes it useful as a metal that preserves its outermost layer from corroding, unlike other metals such as copper, magnesium, and aluminium. Chromium has a melting point of 1907 degrees C, which is relatively low compared to the majority of transition metals. However, it still has the second highest melting point out of all the period 4 elements, being topped by vanadium by 3 degrees C at 1910 degrees C. The boiling point of 2671 degrees C, however, is comparatively lower, having the third lowest boiling point out of the period 4 transition metals alone behind manganese and zinc. The electrical resistivity of lead at 20 degrees C is 125 nanometers. Chromium has an unusually high specular reflection in comparison to that of other transition metals. At 425 μm, chromium was found to have a relative maximum reflection of about 72% reflectance, before entering a depression in reflectivity, reaching a minimum of 62% reflectance at 750 μm before rising again to reflecting roughly 90% of 4000 μm of infrared waves. When chromium is formed into a stainless steel alloy and polished, the specular reflection decreases with the inclusion of additional metals, yet is still rather high in comparison with other alloys. Between 40% and 60% of the visible spectrum is reflected from polished stainless steel. The explanation on why chromium displays such a high turnout of reflected photon waves in general, especially the 90% of infrared waves that were reflected, can be attributed to chromium's magnetic properties. Chromium has unique magnetic properties in the sense that chromium is the only elemental solid which shows antiferromagnetic ordering at room temperature. Above 38 degrees C, its magnetic ordering changes to paramagnetic. The antiferromagnetic properties, which cause the chromium atoms to temporarily ionize and bond with themselves, are present because the body-centric cubic's magnetic properties are disproportionate to the lattice periodicity. This is due to the fact that the magnetic moments at the cube's corners and the cube centers are not equal, but are still antiparallel. From here, the frequency-dependent relative permittivity of chromium, deriving from Maxwell's equations in conjunction with its antiferromagnetivity, leaves chromium with among the highest infrared and visible light reflectances of the known chemical elements. Chromium metal left standing in air is passivated by oxidation, forming a thin, protective, surface layer. This layer is a spinel structure only a few molecules thick. It is very dense, and prevents the diffusion of oxygen into the underlying metal. This is different from the spongy oxide that forms on iron and carbon steel, through which elemental oxygen continues to migrate, reaching the underlying material to cause continued further rusting. Passivation can be enhanced by short contact with oxidizing acids like nitric acid. Passivated chromium is stable against acids. Passivation can be removed with a strong reducing agent that destroys the protective oxide layer on the metal. Chromium metal treated in this way readily dissolves in weak acids. Chromium, unlike such metals as iron and nickel, does not suffer from hydrogen embrittlement. However, it does suffer from nitrogen embrittlement, reacting with nitrogen from air and forming brittle nitrides at the high temperatures necessary to work the metal parts. Naturally occurring chromium is composed of three stable isotopes, 5,2Cr, 5,3Cr, and 5,4Cr, with 5,2Cr being the most abundant. 19 radioisotopes have been characterized, with the most stable being 50Cr with a half-life of 1.8 times 1017 years, and 51Cr with a half-life of 27.7 days. All of the remaining radioactive isotopes have half-lives that are less than 24 hours and the majority less than 1 minute. Chromium also has two metastable nuclear isomers. 5,3Cr is the radiogenic decay product of 5,3Mn. Chromium isotopes are typically collocated with manganese isotopes. This circumstance is useful in isotope geology. Manganese-chromium isotope ratios reinforce the evidence from 26Al and 107Pd concerning the early history of the Solar System. Variations in 53Cr/52Cr and Mn/Cr ratios from several meteorites indicate an initial 53Mn/55Mn ratio that suggests Mn-Cr isotopic composition must result from in situ decay of 5,3Mn in differentiated planetary bodies. Hence 5,3Cr provides additional evidence for nucleosynthetic processes immediately before coalescence of the Solar System. The isotopes of chromium range in atomic mass from 43U to 67U. The primary decay mode before the most abundant stable isotope, 5,2Cr, is electron capture, and the primary mode after is beta decay. 5,3Cr has been posited as a proxy for atmospheric oxygen concentration. Chromium is a member of group 6, of the transition metals. Chromium has an electron configuration of 3d54s1, owing to the lower energy of the high-spin configuration. Chromium exhibits a wide range of oxidation states, but chromium being ionized into a cation with a positive 3 charge serves as chromium's most stable ionic state. The +3 and +6 states occur the most commonly within chromium compounds. Charges of +1, +4, and +5 for chromium are rare, but do nevertheless occasionally exist. A large number of chromium compounds are known, such as chromium nitrate, chromium acetate, and chromium oxide. Chromium can be obtained by dissolving elemental chromium in acids like hydrochloric acid or sulfuric acid, but it can also be formed through the reduction of chromium by cytochrome C7. The Cr3+ ion has a similar radius to Al3+, and they can replace each other in some compounds, such as in chrome alum and alum. When a trace amount of Cr3+ replaces Al3+ in corundum, pink sapphire, or red-colored ruby is formed, depending on the amount of chromium. Chromium tends to form octahedral complexes. Commercially available chromium chloride hydrate is the dark green complex Cl. Closely related compounds are the pale green Cl2 and violet Cl3. If water-free green chromium chloride is dissolved in water, the green solution turns violet after some time as the chloride in the inner coordination sphere is replaced by water. This kind of reaction is also observed with solutions of chrome alum and other water-soluble chromium salts. Chromium hydroxide 3 is amphoteric, dissolving in acidic solutions to form 3+, and in basic solutions to form 3. It is dehydrated by heating to form the green chromium oxide, a stable oxide with a crystal structure identical to that of corundum. Chromium compounds are oxidants at low or neutral pH. Chromate anions and dichromate anions are the principal ions at this oxidation state. They exist at an equilibrium, determined by pH. Chromium halides are known also and include the hexafluoride CrF6 and chromyl chloride. Sodium chromate is produced industrially by the oxidative roasting of chromite ore with calcium or sodium carbonate. The change in equilibrium is visible by a change from yellow to orange, such as when an acid is added to a neutral solution of potassium chromate. At yet lower pH values, further condensation to more complex oxyanions of chromium is possible. Both the chromate and dichromate anions are strong oxidizing reagents at low pH. They are, however, only moderately oxidizing at high pH. Chromium compounds in solution can be detected by adding an acidic hydrogen peroxide solution. The unstable dark blue chromium peroxide is formed, which can be stabilized as an ether adduct Cro5 or 2. Chromic acid has the hypothetical formula H2CrO4. It is a vaguely described chemical, despite many well-defined chromates and dichromates being known. The dark red chromium oxide CrO3, the acid anhydride of chromic acid, is sold industrially as chromic acid. It can be produced by mixing sulfuric acid with dichromate, and is a strong oxidizing agent. The oxidation state +5 is only realized in few compounds but are intermediates in many reactions involving oxidations by chromate. The only binary compound is the volatile chromium fluoride. This red solid has a melting point of 30 degrees C and a boiling point of 117 degrees C. It can be prepared by treating chromium metal with fluorine at 400 degrees C and 200 bar pressure. The Peroxy Chromate is another example of the +5 oxidation state. Potassium Peroxy Chromate 4 is made by reacting potassium chromate with hydrogen peroxide at low temperatures. This red-brown compound is stable at room temperature but decomposes spontaneously at 150–170 degrees C. Compounds of chromium are slightly more common than those of chromium. The tetrahalides, CrF4, CrCl4, and CrBr4, can be produced by treating the trihalides with the corresponding halogen at elevated temperatures. Such compounds are susceptible to disproportionation reactions and are not stable in water. Many chromium compounds are known, such as the water-stable chromium chloride CrCl2 that can be made by reducing chromium chloride with zinc. The resulting bright blue solution created from dissolving chromium chloride is only stable at neutral pH. Some other notable chromium compounds include chromium oxide Cro, and chromium sulfate CrSO4. Many chromous carboxylates are known as well, the most famous of these being the red chromium acetate 4, that features a quadruple bond. Most chromium compounds are obtained solely by oxidation of electron-rich, octahedral chromium complexes. Other chromium complexes contain cyclopentadienyl ligands. As verified by X-ray diffraction, a CR-CR quintuple bond PM has also been described. Extremely bulky monodentate ligands stabilize this compound by shielding the quintuple bond from further reactions. Many chromium compounds are currently known, however, most of these compounds are derivatives of the compounds chromium hexacarbonyl or bischromium. Chromium is the 13th most abundant element in Earth's crust with an average concentration of 100 ppm. Chromium compounds are found in the environment from the erosion of chromium-containing rocks, and can be redistributed by volcanic eruptions. Typical background concentrations of chromium in environmental media are: atmosphere 10 ngm3, soil 500 mg/kg1, vegetation 0.5 mg/kg1, freshwater 10 ugl1, seawater 1 ugl1, sediment 80 mg/kg1. Chromium is mined as chromite ore. About 2/5 of the chromite ores and concentrates in the world are produced in South Africa, about a third in Kazakhstan, while India, Russia, and Turkey are also substantial producers. Untapped chromite deposits are plentiful, but geographically concentrated in Kazakhstan and southern Africa. Although rare, deposits of native chromium exist. The Udakhnaya pipe in Russia produces samples of the native metal. This mine is a kimberlite pipe, rich in diamonds, and the reducing environment helped produce both elemental chromium and diamond. The relation between Cr and Cr strongly depends on pH and oxidative properties of the location. In most cases, Cr is the dominating species, but in some areas, the groundwater can contain up to 39 g/liter of total chromium, of which 30 g/liter is Cr. Chromium was first discovered as an element after it came to the attention of the Western world in the red crystalline mineral Crocoite chromate. This mineral was discovered in 1761 and was initially used as a pigment. The distinctive color was attributed to the chromium from within the crocoite. In present day, nearly all chromium is commercially extracted from the only viable ore for extensiveness and predicted long-term use, being chromite, which is iron chromium oxide. Chromite is now the principal source of chromium for use in pigments. Weapons found in burial pits dating from the late 3rd century BC Qin dynasty of the Terracotta Army near Xi'an, China, have been analyzed by archaeologists. Although these weapons were presumably buried more than 2 millennia ago, the ancient bronze tips of both the swords and crossbow bolts found at the site showed unexpectedly little corrosion, possibly because the bronze was deliberately coated with a thin layer of chromium oxide. Still, this oxide layer that was found on the weapons was not pure chromium metal or chrome plating as it is commonly produced today, but a mere 10 to 15 μm layer of chromium oxide molecules at up to 2% chromium was discovered, which turned out to be enough to protect the bronze from corroding. Chromium minerals as pigments came to the attention of the West in the 18th century. On July 26, 1761, Johann Gottlob Lehmann found an orange-red mineral in the Beryozovskoye mines in the Ural Mountains which he named Siberian red lead. Though misidentified as a lead compound with selenium and iron components, the mineral was in fact crocoite chromate, with the formula of PbCrO4. In 1770, Peter Simon Pallas visited the same site as Lehmann and found a red lead mineral that was discovered to possess useful properties as a pigment in paints. After Pallas, the use of Siberian red lead as a paint pigment began to develop rapidly throughout the region. In 1794, Louis Nicolas Vauquelin received samples of crocoite ore. He produced chromium trioxide by mixing crocoite with hydrochloric acid. In 1797, Vauquelin discovered that he could isolate metallic chromium by heating the oxide in a charcoal oven, for which he is credited as the one who truly discovered the element. Vauquelin was also able to detect traces of chromium in precious gemstones, such as ruby or emerald. During the 19th century, chromium was primarily used not only as a component of paints, but in tanning salts as well. For quite some time, the crocoite found in Russia was the main source for such tanning materials. In 1827, a larger chromite deposit was discovered near Baltimore, United States, which quickly met the demand for tanning salts much more adequately than the crocoite that had been used previously. This made the United States the largest producer of chromium products until the year 1848, when larger deposits of chromite were uncovered near the city of Bursa, Turkey. Chromium is also famous for its reflective, metallic luster when polished. It is used as a protective and decorative coating on car parts, plumbing fixtures, furniture parts, and many other items, usually applied by electroplating. Chromium was used for electroplating as early as 1848, but this use only became widespread with the development of an improved process in 1924. Approximately 28.8 million metric tons of marketable chromite ore was produced in 2013, and converted into 7.5 mt of ferrochromium. According to John F. Papp, writing for the USGS, ferrochromium is the leading end use of chromite ore. Stainless steel is the leading end use of ferrochromium. The largest producers of chromium ore in 2013 have been South Africa, Kazakhstan, Turkey, India, with several other countries producing the rest of about 18% of the world production. The two main products of chromium ore refining are ferrochromium and metallic chromium. For those products, the ore smelter process differs considerably. For the production of ferrochromium, the chromite ore is reduced in large scale in electric arc furnace or in smaller smelters with either aluminium or silicon in an aluminothermic reaction. For the production of pure chromium, the iron must be separated from the chromium in a two-step roasting and leaching process. The chromite ore is heated with a mixture of calcium carbonate and sodium carbonate in the presence of air. The chromium is oxidized to the hexavalent form, while the iron forms the stable Fe2O3. The subsequent leaching at higher elevated temperatures dissolves the chromates and leaves the insoluble iron oxide. The chromate is converted by sulfuric acid into the dichromate. The dichromate is converted to the chromium oxide by reduction with carbon and then reduced in an aluminothermic reaction to chromium. The creation of metal alloys account for 85% of the available chromium's usage. The remainder of chromium is used in the chemical, refractory, and foundry industries. The strengthening effect of forming stable metal carbides at the grain boundaries and the strong increase in corrosion resistance made chromium an important alloying material for steel. The high-speed tool steels contain between 3 and 5% chromium. Stainless steel, the primary corrosion-resistant metal alloy, is formed when chromium is introduced to iron in sufficient concentrations, usually where the chromium concentration is above 11%. For stainless steel's formation, ferrochromium is added to the molten iron. Also, nickel-based alloys increase in strength due to the formation of discrete, stable metal carbide particles at the grain boundaries. For example, Inconel 718 contains 18.6% chromium. Because of the excellent high-temperature properties of these nickel superalloys, they are used in jet engines and gas turbines in lieu of common structural materials. The relative high hardness and corrosion resistance of unalloyed chromium makes chrome a reliable metal for surface coating. It is still the most popular metal for sheet coating with its above-average durability compared to other coating metals. A layer of chromium is deposited on pretreated metallic surfaces by electroplating techniques. There are two deposition methods, thin and thick. Thin deposition involves a layer of chromium below 1 m thickness deposited by chrome plating, and is used for decorative surfaces. Thicker chromium layers are deposited if wear-resistant surfaces are needed. Both methods use acidic chromate or dichromate solutions. To prevent the energy-consuming change in oxidation state, the use of chromium sulfate is under development. For most applications of chromium, the previously established process is used. In the chromate conversion coating process, the strong oxidative properties of chromates are used to deposit a protective oxide layer on metals like aluminium, zinc, and cadmium. This passivation and the self-healing properties by the chromate stored in the chromate conversion coating, which is able to migrate to local defects, are the benefits of this coating method. Because of environmental and health regulations on chromates, alternative coating methods are under development. Chromic acid anodizing of aluminium is another electrochemical process, which does not lead to the deposition of chromium, but uses chromic acid as electrolyte in the solution. During anodization, an oxide layer is formed on the aluminium. The use of chromic acid, instead of the normally used sulfuric acid, leads to a slight difference of these oxide layers. The high toxicity of CR compounds, used in the established chromium electroplating process, and the strengthening of safety and environmental regulations demand a search for substitutes for chromium, or at least a change to less toxic chromium compounds. The mineral crocowhite was used as a yellow pigment shortly after its discovery. After a synthesis method became available starting from the more abundant chromite, chrome yellow was, together with cadmium yellow, one of the most used yellow pigments. The pigment does not photodegrade, but it tends to darken due to the formation of chromium oxide. It has a strong color, and was used for school buses in the United States and for the postal service in Europe. The use of chrome yellow has since declined due to environmental and safety concerns and was replaced by organic pigments or other alternatives that are free from lead and chromium. Other pigments that are based around chromium are, for example, the deep shade of red pigment chrome red, which is simply lead chromate with lead hydroxide too. A very important chromate pigment, which was used widely in metal primer formulations, was zinc chromate, now replaced by zinc phosphate. A wash primer was formulated to replace the dangerous practice of pre-treating aluminium aircraft bodies with a phosphoric acid solution. This used zinc tetroxy chromate dispersed in a solution of polyvinyl butyryl. An 8% solution of phosphoric acid in solvent was added just before application. It was found that an easily oxidized alcohol was an essential ingredient. A thin layer of about 10–15 m was applied, which turned from yellow to dark green when it was cured. There is still a question as to the correct mechanism. Chrome green is a mixture of Prussian blue and chrome yellow, while the chrome oxide green is chromium oxide. Chromium oxides are also used as a green pigment in the field of glass making and also as a glaze for ceramics. Green chromium oxide is extremely light fast and as such is used in cladding coatings. It is also the main ingredient in infrared reflecting paints, used by the armed forces to paint vehicles and to give them the same infrared reflectance as green leaves. Natural rubies are corundum crystals that are colored red due to chromium ions. A red-colored artificial ruby may also be achieved by doping chromium into artificial corundum crystals, thus making chromium a requirement for making synthetic rubies. Such a synthetic ruby crystal was the basis for the first laser, produced in 1960, which relied on stimulated emission of light from the chromium atoms in such a crystal. A ruby laser is lasing at 694.3 nanometers, in a deep red color. Because of their toxicity, chromium salts are used for the preservation of wood. For example, chromate copper arsenate is used in timber treatment to protect wood from decay fungi, wood-attacking insects, including termites, and marine borers. The formulations contain chromium based on the oxide CrO3 between 35.3% and 65.5%. In the United States, 65,300 metric tons of CCA solution were used in 1996. Chromium salts, especially chrome alum and chromium sulfate, are used in the tanning of leather. The chromium stabilizes the leather by cross-linking the collagen fibers. Chromium tanned leather can contain between 4 and 5% of chromium, which is tightly bound to the proteins. Although the form of chromium used for tanning is not the toxic hexavalent variety, there remains interest in management of chromium in the tanning industry. Recovery and reuse, direct/indirect recycling, use of less chromium, or chrome-less tanning are practiced to better manage chromium in tanning. The high heat resistivity and high melting point makes chromite and chromium oxide a material for high-temperature refractory applications, like blast furnaces, cement kilns, molds for the firing of bricks and as foundry sands for the casting of metals. In these applications, the refractory materials are made from mixtures of chromite and magnesite. The use is declining because of the environmental regulations due to the possibility of the formation of chromium. Several chromium compounds are used as catalysts for processing hydrocarbons. For example, the Phillips catalyst, prepared from chromium oxides, is used for the production of about half the world's polyethylene. FeCr mixed oxides are employed as high-temperature catalysts for the water-gas shift reaction. Copper chromite is a useful hydrogenation catalyst. In the form trivalent chromium, Cr, or Cr3+, chromium was tentatively identified as an essential nutrient in the late 1950s and later accepted as a trace element for its roles in the action of insulin, a hormone critical to the metabolism and storage of carbohydrate, fat, and protein. The precise mechanism of its actions in the body, however, have not been fully defined, leaving in question whether chromium is essential for healthy people. Trivalent chromium occurs in trace amounts in foods, wine, and water. In contrast, hexavalent chromium, or Cr6+, is highly toxic and mutagenic when inhaled. Ingestion of chromium in water has been linked to stomach tumors, and it may also cause allergic contact dermatitis. Chromium deficiency, involving a lack of Cr in the body, or perhaps some complex of it, such as glucose tolerance factor, is controversial. Some studies suggest that the biologically active form of chromium is transported in the body via an oligopeptide called low molecular weight chromium binding substance, which might play a role in the insulin signaling pathway. Chromium content of common foods is generally low. Chromium content of food varies widely due to differences in soil mineral content, growing season, plant cultivar, and contamination during processing. In addition, chromium leach into food cooked in stainless steel, with the effect largest when the cookware is new. Acidic foods such as tomato sauce, which are cooked for many hours, also exacerbate this effect. There is disagreement on chromium's status as an essential nutrient. Governmental departments from Australia, New Zealand, India, Japan, and the United States consider chromium essential, while the European Food Safety Authority, representing the European Union, does not. The National Academy of Medicine updated the estimated average requirements and the recommended dietary allowances for chromium in 2001. For chromium, there was not sufficient information to set EARs and RDAs, so its needs are described as estimates for adequate intakes. The current ACE of chromium for women ages 14 through 50 is 25 μg/day, and the ACE for women ages 50 and above is 20 μg/day. The ACE for women who are pregnant are 30 μg/day, and for women who are lactating, the set ACE are 45 μg/day. The ACE for men ages 14 through 50 are 35 μg/day, and the ACE for men ages 50 and above are 30 μg/day. For children ages 1 through 13, the ACE increase with age from 0.2 μg/day up to 25 μg/day. As for safety, the NOM sets tolerable upper intake levels for vitamins and minerals when the evidence is sufficient. In the case of chromium, there is not yet enough information and hence no goal has been established. Collectively, the EARs, RDAs, ACE and ULs are the parameters for the nutrition recommendation system known as Dietary Reference Intake. Australia and New Zealand consider chromium to be an essential nutrient, with an AI of 35 μg/day for men, 25 μg/day for women, 30 μg/day for women who are pregnant, and 45 μg/day for women who are lactating. AOL has not been set due to the lack of sufficient data. India considers chromium to be an essential nutrient, with an adult recommended intake of 33 μg/day. Japan also considers chromium to be an essential nutrient, with an AI of 10 μg/day for adults, including women who are pregnant or lactating. AOL has not been set.